All right, so those are examples that you might see dealing with just perpendicular bisectors. Yeah, we started a little bit with triangles here, but that was to be able to tell if it's a perpendicular bisector. This is where we switch topics a little bit, just slightly for now. We will go back to being perpendicular bisectors, but right now I have to talk about what lines being concurrent means. Because your theorems for the next 3 sections will talk about the point of concurrency of perpendicular lines. And you need to know what concurrent is. When 3 or more lines, rays, or segments intersect in the same point, they are called concurrent lines, rays, or segments. So if I look here, these 4 lines intersect at this one point right here. So these 4 lines are concurrent. They intersect at one point. These 3 lines over here intersect at 3 different points. They're not concurrent lines. So it's a very fancy way of saying, hey, all these lines intersect at one point. It's one word instead of a sentence. So, concurrent lines, point of concurrency is the point that the lines are concurrent. Alright, there's not exactly an example I want to do with Concept 7, you just need to know it. Concept 8, we talk about a point of concurrency. In particular, we talk about the circumcenter. Concurrency of perpendicular bisectors of a triangle is the actual theorem. I didn't want to put that in the title, it was a lot of words. But this is the next theorem, concurrency of perpendicular bisectors of a triangle. The perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of a triangle. Oh, so what that's saying is, if I look at this triangle over here, these blue lines, they're all perpendicular bisectors. They're all labeled as perpendicular, and they're all marked as bisectors. So therefore, each of these blue lines is a perpendicular bisector. If I think back to the last theorem, a point on this blue line will always be equidistant from its endpoints. So if I look, this point is on this perpendicular bisector, so by the perpendicular bisectors theorem, this point has to be the same distance from here to the vertex over here as it is from this point to the vertex over here. That's just talking about this blue line right here. Alright, but what about this perpendicular bisector over here? Well, the same thing. It has to be the same distance from this point to the corner as it is from this point to the corner. So this length, this red length, and this red length all have to be the same. So we can summarize that a little bit easier and say the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. So this point will be the same distance to the corner here as it is from this corner and this corner here, always. You'll see in example problem 6 how this could be used. I'm not going to go there just yet. But here's the really neat thing. This point of concurrency, if I would draw a circle with radius of this red line here, what I would see is that this here would happen. So if I would go from the point of concurrency called the circumcenter in this case, and it goes from point P to point C is the radius, well, that circle will perfectly circumscribe. It's completely on the outside of the triangle, but intersects only at the vertices of the triangle. You could also say this triangle is inscribed, just like the circle is circumscribed. But yeah, I've got a neat demonstration behind me, so let's see it. Alright, something really neat is this triangle, first of all. It's a sweet looking triangle. I think I did a very good job. Now what I've done is I've made 3 perpendicular bisectors. One that goes through point F here, which is a midpoint, as you can see down here. I tell you the length is 3.31 centimeters or 3.31 centimeters. So this length here is 3.31. This one here is 3.31. Same thing with this side over here. It's just so that we can visually see that it is a bisector. Now if I look here, all the angles that the perpendicular these lines intersect at are perpendicular. So in this case, all the red lines here are perpendicular bisectors. This one, line EG, is a perpendicular bisector of this side over here. Line GF is a perpendicular bisector of this side, and so on and so forth. They will always intersect here. No matter where I move it, they will always intersect. And sometimes this center is outside of the circle. Whoa. Sometimes it's inside, and sometimes it's right on the edge. So this center of a triangle doesn't actually have to be in the middle of the triangle. In fact, look at how far out I can push this. I can push it all the way to the edge of the screen here. So, I mean, and that's not the furthest I can push it. I can push it even further away and further away. You can't even see it anymore, but it's way over to the left. Yeah, to the left. I can also have it go the other way. Yep, this way. Now, if you look, if one of the angles is obtuse, the center will be outside. In this case, when I had it over here, when I pushed this angle to be obtuse, the circumcenter went outside of the triangle. And when it's a right angle, right there, then the circumcenter will be on the center. Sorry, it'll be on one of the sides. And whenever the triangle is all acute angles, the center will be on the inside. And this isn't even the most amazing part. Something you didn't see because I had it all the way over to the left here. I don't want to grab the line too. But over here, these lengths right here, they have stayed the same the whole time. No matter where I've moved this point, those three are the same. So from G to A, it's the same length as G to C. No matter where I move it. And the really neat part is if I take a circle here, I start to center here, and I'm starting to construct a circle. So I can choose its radius. If I bring this radius all the way over to this vertex, this green circle completely keeps this center here on the inside. So I look, these perpendicular bisectors intersect at G, which creates a green circle that will always be at the vertices of the triangle. It doesn't matter how I move this triangle. I can move it any way I want, but this green circle will always keep the triangle on the inside. And I think it's kind of neat. But there you go. That's the circumcenter. It's always going to be the same distance from the circumcenter to the vertices, which has some applications which I'll talk about shortly. At this point, we're going to jump ahead to section 6. Sorry, not section 6. Example 6. And that's because I want to talk about the application. You own a business that has 3 stores. The stores require that you have a warehouse. Maybe it's a distribution company, maybe it's something just where you store stuff. And you want one warehouse that is the same distance from all 3 of your stores. How would you find the location that is the same distance from each store? Wait a second. I want to find something that's the same distance from each store. Wouldn't that be as simple as plotting your 3 points on a grid and then using the perpendicular bisector to find that one point, point P, let's just say, that's the same distance from each of my stores A, B, and C? Well, yeah, that's it. The circumcenter here will be the same distance away from A as it is from B as it is from C. So what I would do in example problem 6 is I draw the triangle. I would draw the perpendicular bisectors. Wherever those 3 perpendicular bisectors intersect is the spot I should build my building, if I want it to be the same distance from all 3 stores. There are definitely other applications. I'll leave it up to you to find them. But let's do an example problem where we have to do some math, where we have to do some calculations. Find the value of segment EG. Find the value of the length of segment EG, length of segment AG, and the length of segment BG if all the blue segments are perpendicular bisectors of a side. So I look at this picture. This is a triangle. Great. These blue segments are perpendicular bisectors. So even though it's not labeled, I know it's a perpendicular bisector. So let's draw the picture. Alright, now that I have redrawn the picture, I'm going to fill in everything I know. Well, if all the blue lines are perpendicular bisectors, these could all be different lengths, the blue lines. However, G is the circumcenter, which means all the red lines, the lines from the circumcenter to the vertex, all have to be the same length. So I automatically know this has to be 20, and I automatically know that this has to be 20. And I look, oh, that's actually two of my answers. I was looking for that. AG has to be 20, and length of segment BG has to be 20. Two of my answers. Just as simple as knowing that circumcenter has to be the same distance from A as it is from C as it is from B. But now comes the hard part. How do I find this length? Oh, I think I see it now. This here is perpendicular. This is a right angle. I'm going to erase the parts that I no longer need. So watch carefully. I'm going to erase this part up to the blue line. And I'm going to stop erasing there. Then I'm going to erase this red line up to this circumcenter. I'm going to erase this corner of the triangle. And I'm going to leave this alone. And yeah, I erased G, but this is G here. And I look, it's a right triangle. I'm looking for the third length of a right triangle. A squared plus B squared equals C squared. This is Pythagorean's theorem. It's actually officially introduced, I believe, in chapter 7. You should know it from last year, but let's use it anyway. A squared and B squared are the legs of a right triangle, so that means A could be X, and B could be 16, and C here has to be the hypotenuse, in this case 20. And at this point, it's just as simple as solving for X. X squared is X squared, 16 squared is 16 times 16, 256 if I remember correctly. And 20 squared is 20 times 20, or 400. And there I go. Solving for x squared, I subtract 256 from both sides, and if done correctly, I believe I get 144. At this point, you take the square root of both sides, and I get x to be technically plus or minus 12, because whenever you take the square root of both sides, you should consider plus or minus. However, a length can never be negative, so therefore positive 12 is the only reasonable answer. Ooh, why did I box that up? I found x, but I was looking for length of segment EG. And there you go. Problem is done. So this is perpendicular bisectors and how they can be used in a triangle. The three perpendicular bisectors of a triangle always intersect at a point that we call the circumcenter. And that circumcenter is always the same distance away from each vertex. Till next time.